about it and say what we know about it. The function again is y equals 1 over x. And so if I want to sketch a graph of y equals 1 over x, well, I'll put my axes down. And again, I can do, inputs and outputs. You could do this for any graph. And so if I input 1, the output is 1. Or if I input 2, the output is a half, right? So here's 1 comma 1. Here's 2 comma 1 half, right? But what you guys told me is that you're going to have a vertical asymptote at x equals 0. And maybe to see that, you have to put in inputs that are closer to 0. Like what? I can't put in 0, right? 0 is not in the domain.
0.001.
Okay, so we put in our favorite seal number, 0.001, right? And so what's the output then? Well, that's 1/1000th, so the output would be 1,000, right? Or even if you put in 0.1, the output is 10. If you put in a fraction like 1/2, the output is 2. And so the reason you get an asymptote is because as x gets closer and closer to 0, the outputs, how are we going to say this? The outputs, and here's some nice phrasing maybe, grow without bound as x approaches 0. Now I better be very careful here. It's as x approaches 0 from which side? From the right. Do you remember how to symbolize that? You put a little plus sign up here. Okay? And you really ought to do that, right? Are you with me? And the reason I say that is because you can also put in negative inputs. Here, let me do that. If I were to throw -1 in here, I get -1. Or if I throw in -1/2, I get -2. And so on this side, you get a mirror image, don't you? Y equals 1 over x. You get a mirror image on this side. And so we might say they, I don't know, shrink without bound or decay without bound. I don't know. It's something different on the left-hand side. You guys with me? Now what happens is, in this section that we're covering today, we're talking about infinite limits. Maybe I should list that. This is 2.4, right guys? Infinite limits. And some of this is just honestly language. You've studied asymptotes before. You've studied functions like 1 over x before. But what we're going to say, in order to say that the outputs grow without bound, we have new language for that. We're going to say the limit as x approaches 0 from the right-hand side of the function 1 over x, we're going to write that that's positive infinity. And what this means, for now, verbally, is this statement. The outputs grow without bound as x approaches 0 from the right-hand side. I think that's a nice way to say it. So then, like I said, how are we going to say this, what's happening over here? Well, I guess a couple things I can say. First of all, I'll say the limit as x approaches 0, and I'll put the negative sign, right? Because I'm talking about what happens as I come in from the left-hand side. And again, my function is 1 over x. And so what am I going to say? Well, here the outputs get smaller without bound. So all we're going to do is we're going to put a negative sign in front of our infinity. That's right. And what that means, I guess I would say it this way, the outputs get smaller without bound. Does that make sense to you guys? Okay. The outputs get smaller without bound. Okay. Does y equal 1 over x have another asymptote? It doesn't have another vertical asymptote. Go ahead. Wait, give me the name.
Jacob.
Jacob, go ahead.
Y equals 0.
Y equals 0 is also an asymptote. You guys with me on that? So let me talk just a little bit about the line y equals 0 being an asymptote. And really, that's section 2.5. Section 2.5 is called limits at infinity. And I know this is what you guys are reading for Friday. Okay. And we're supposed to cover it on Friday. Actually, on Friday, I'm going to do another group work, and I'm going to have kind of a worksheet that deals with both kinds of asymptotes. Okay? Limits at infinity. So just so we kind of understand what we're studying here. When we study infinite limits, we're going to be talking about horizontal asymptotes. No. Today we're talking about, vertical asymptotes. Let me get that right. When we talk about limits at infinity, we're going to be talking about horizontal asymptotes. So maybe I'll just give you a little bit of that now while this is on the board. There's a few more outputs that might make sense to do. What happens if you put in something like 10? What's the output? Well, 1/10, right? Or if you put in 1,000, 1/1000th. So as I put larger and larger inputs in to the function 1 over x, I'm getting smaller and smaller values, getting closer and closer to what? Getting closer and closer to 0, right? And so we have a way we're going to say that also. We're going to say that the limit as x approaches infinity, okay, of 1 over x is going to be 0. And I guess all you really need to know for now is what I'm saying is we have a horizontal asymptote in that case. As x gets close to infinity, 1 over x is getting closer and closer to 0. And you can get it as close to 0 as you want. And this is an important idea. If I said, hey, I want you to be within 1/1,000,000th of 0, can you do it? Can you give me an input that's going to do that? You just have to make sure your input is bigger than what? If I want to be smaller than 1/1,000,000th, you got to make sure that your input is larger than 1,000,000. Take 1,000,000,000, right? And you're there. You can get arbitrarily close. When we talk about limits, you're going to see this phrase, arbitrarily close. And next week, we're going to give you the formal definition that Cauchy came up with 150 years after Newton and Leibniz. That captures this idea of being arbitrarily close. But it's good to talk about asymptotes now. Now, there is one other asymptote that you're going to read about for Friday, so I may as well mention it while I'm on the subject. How many have heard of slant asymptotes? A few remember this, okay. So I may have to do more with this on Friday, we'll see. But I don't have any slant asymptotes for y equals 1 over x, but it turns out that some curves don't get close to a horizontal line, but they get close to some other line. And we'll talk about that more on Friday, okay? Slant asymptotes, I guess this is a type of what we call end behavior. When you see the words, I'm trying to give you guys a taste of the vocabulary because the reading in this book can be tough otherwise. When you see the words end behavior, what that means is what happens as x approaches infinity or negative infinity. End behavior. What's the end behavior for this function? Well, for this function, as x approaches infinity, 1 over x approaches 0. Okay? Or as x approaches negative infinity, 1 over x, what does it approach? What happens if you put in something really negative? Well, like if you put in negative 100, where are you at? You're getting close to 0 also. So this is also going to be 0. This is also going to be 0. And so I guess if I were to kind of complete the graph of 1 over x, well, that's what it looks like. It has a, let me go back to the picture. It has a vertical asymptote and it has a horizontal asymptote. The end behavior is that it equals 0. Okay? But it's funny because I just spent maybe 10, 15 minutes talking. And if I spent 15 minutes, I think 10 of those minutes were on the next section, right? So what's with this section? We're not talking about end behavior here. Here, when we say infinite limits, we're talking about the limit as x approaches some value of a, right? Of f of x. The question is, does it equal infinity? That's the question. Now, what would that even mean? Well, it turns out that we're going to say, in our first example that I just gave you, the limit as x approaches 0 of 1 over x, I'm going to say is undefined. Why? Why would I say that? There is an asymptote, but I'm going to say the limit is undefined. Give me the name.
Sam?
Sam, go ahead.
Is it because you're putting a 0 in the denominator?
So if I put a 0 in the denominator, 1 over 0 is undefined. I agree with that, right? I agree with that. However, we've seen cases. Let me show you that group work again. What did we say about this problem 1?
It's got to be 0.
The limit as x approaches 1. Here's one that gave me 0 in the denominator too, right?
It's 0.
But I got a 0 in the numerator, so I got 1/2, right? And give me the name. What is it?
Nikolai?
Nikolai, go ahead.
It's undefined because there's a jump discontinuity. We don't deduct all at 0.
It is what's called a jump discontinuity. Okay? Now, that's other language, and so I want to make sure people know what Nikolai's saying here. The word he used was jump discontinuity. Jump discontinuity. You see, the problem is, if we want the limit to exist, we need the right-hand limit to be exactly the same as what? the left-hand limit. What did we say the right-hand limit was? Positive infinity, right? But what's the left-hand limit? So when these two are not the same, we're going to say that the limit does not exist. Even if we're talking using this infinity symbols, we're still going to play that game. Okay? Whereas, when you look at this example here, x minus 1 over x squared minus 1. I didn't draw a graph for you, did I? I did not draw a graph. Actually, I can right now. Because, see this equal sign? What we did was we canceled some factors. And so really, that graph there in green is almost exactly the same as the original function in black. The only thing was I canceled a factor. Here, let me go ahead and draw a picture of that green function. Hey, good thing I did 1 over x, because if it's 1 over x plus 1, isn't that almost exactly the same as 1 over x? There's only one difference. When you look at 1 over x plus 1, where is the vertical asymptote for 1 over x plus 1? It's at -1, right? It's at -1. So if I graph, I need to have an asymptote at x equals -1. Notice if I throw a 0 in for x, I'm at the point 0, 1, right? So here, I'm going to graph, and you could try this, f of x equals x minus 1 over x squared minus 1. Maybe graphing calculator might be worth my time. Let's show you this. I know what it looks like, but I want you to see it. Let's graph the function. Y equals, open parentheses, x minus 1 divided by, open parentheses, x squared minus 1. Right? And let's just do the standard zoom. Choice 6, just the standard window, and there it is. Ooh. Well, that's it. It looks kind of like a heart murmur to me, right? Let's try this. Let's zoom in and get a better picture. Okay. So we do have this 1 over x kind of behavior. That's actually a hyperbola, is what the shape is. And it tried to draw the asymptote for me. And so, if I graph it, well, it looks like this, it looks like this, it looks like this. Oh, wait a minute. Let me do this. Table, second graph. Where do you notice this thing is undefined? It's undefined where? -1 I knew about. That was an asymptote. But it's also undefined where? 1. It's undefined at 1. How come? Because if you put in a 1, what happens to the denominator? You get 0, right? You get 0 over 0. So it turns out that what we showed last time was, hey, you can do some canceling. Okay? And this idea of canceling, what you're really doing, when you get 1 over x plus 1, the graph would look exactly the same as the other one. The only difference is 1 over x plus 1 is defined at 1, right? And what's the value? Well, 1/2. You kind of color that in. The act of coloring that hole in, that's what makes this what's called a removable discontinuity. A removable discontinuity. That's a word I haven't used until today when Nikolai said it. Discontinuity. But what's the root word of discontinuity? What word is buried in there that we have used? Continuity. Continuous, right? And maybe I should say that one more time. What does it mean to be continuous? Well, that's coming up, right? I mean, look at the lesson plan for the week. 2.4, 2.5, and I'll tell you that 2.6 is all about continuity. Okay? And I'll give you the definition again here. We say f of x is continuous at x equals a if the limit as x approaches a of f of x equals, what do we always try first? We always try plugging in the a. This is my definition of continuous. Continuous. You'll read that when you read that section 6 for next Monday. Okay? So a lot of places we're continuous, but I guess what we're studying this week is what can happen if you're not continuous. You can have a removable discontinuity, like when we had 0 over 0. You can have a jump discontinuity, and then you don't have a limit existing. So we said the limit does not exist. Okay? So two different situations. All right. I still didn't go back to the problems up on the board. Oh, yeah. Well, we said that the limit as x goes to 0 of sine of 1 over x on the board, or pi over x, the reason it doesn't exist is because, well, sometimes it'll equal 0, sometimes it'll equal -1, +1. We know that sine fluctuates, right? The sine function fluctuates between what and what?
1 and -1.
Yeah, between 1 and -1. Okay? And so that's one of the things that was being talked about in the book. But here's something that was in the book. That number 2 on the board, they talk about x squared times the sine of 1 over x. Here it is. Example 8. Applying the squeeze theorem. So B up there says, use the squeeze theorem to verify that this limit actually equals 0. So we want to talk about that. Why does this one equal 0? Why? Well, here's why. Let's go through it a little bit. They have a solution here. For any real number, it says that sine is going to be between -1 and 1. We know that, right? So when I look at the function x squared times sine of 1 over x, see, if you multiply through the inequality by x squared, you get this inequality. And so I think it's kind of interesting what they do here. They say, let's take a look at, again, we're trying to figure out the sine of 1 over x, right, times x squared. This is my new function. And what happens as x approaches 0? Well, we know sine of 1 over x is between 1 and -1. So negative x squared is less than or equal to the function I'm interested in, less than or equal to x squared. You just multiply through by x squared. And what you do now is you look at two functions. We're going to look at what happens to x squared as x goes to 0. Well, that's easy, right? It's a parabola. And they show you on the picture. Look, it's in red, right? You can zoom in. As x gets really close to 0, like 0.05, the red parabola is getting really close to 0. Right? So, let me make this a little smaller so we can keep looking at that. Right? The limit as x approaches 0 of x squared is 0. Okay? And we also know that the limit as x approaches 0 of negative x squared equals 0. Right? And what we're interested in is, what is the limit as x approaches 0 of this? X squared sine of 1 over x. Well, this is what's known as the squeeze theorem. You see, we know that as x gets small, this is going to approach 0. That's the red parabola. And we know that as x gets small, this is going to approach 0. Right? And so, it stands to reason that the limit as x approaches 0 of x squared sine of 1 over x has to be between 0 and 0. So what's the only possibility? 0. This is a very nice example of what's known as the squeeze play. Oh no, that's when you bunt with a guy on third. This is the squeeze theorem, right? All right, the tribe lost last night, but you can give me a break. I tried. The squeeze theorem, right? So we have zeros, and so since I know that that's between, that limit must also be 0. And it was from last section, but I thought, you know, I want to make sure you guys get a taste of that. The fact that it says theorem means it's been proven, okay, to work, and it's a theorem that we're going to use later in the course. So I wanted to make sure that I mentioned it while we're here. There's a couple things that make this tough. It says, use the factorization formula, x to the n minus a to the n equals this big mess. That big mess. And so I wanted to see partly, can you follow what a big formula like this says? So in order to use this big formula right here, right, one thing I need to decide is, what does n equal for my case? N equals what? 5. Right? That's clear. N equals 5. And so if I try to follow that formula with n equaling 5, let's see if I can. So we're going to take that x to the n minus a to the n. See, the whole idea is that if you have x to the n minus a to the n, you can always factor it as x minus a times something else. X minus a times something else. And that's good for this problem, because then what am I going to do in the very next step? I'm going to cancel out the x minus a's. And then I'll be in good shape. Right now I can't put an a in. It'd be undefined. This is removing the discontinuity here. Okay? But using that formula up above is well, that's a challenge right there. By the way, this formula is not totally out there. Let me show you what I mean. You guys, do you guys know how to factor? Just for example, we'll kind of do this up here on the side and come back. We know that x squared minus a squared can be factored as x minus a times what?
A plus A.
Yep, x plus a. Right? That is actually an example of my formula. It's just that n equals what there? N equals 2. See, if you think about n equaling 2, then what you're doing is you're doing, well, x to the 2 minus 1 and a to the 2 minus 1. But what's 2 minus 1 is 1, so we don't write it down. Are you guys with me on this? Or I remember last time on the group work, last Friday, there was a problem where I had x cubed minus, I forget if it was 8. Yeah, it was 8. 8, of course, is also a perfect cube. What is it? 2 cubed, right? So we wrote it as x minus 2, and it was x squared plus 2x plus 4. But let me just say that that could also be done using this very general formula up above. You would just have to, since n, what does n equal in this example? N equals 3 here, so that's why this is 3 minus 1 is 2. And then you do 3 minus 2 is 1. So the powers of x go down, and the powers of a go up as you use the formula. So let me try to do now our problem. Problem, what number is this, guys? 71, thanks. So we're trying to do problem 71. And so I'm trying to use that formula up above. And so the very first thing I should write down is x to the n minus 1. And again, I'm noticing that n equals 5. And so I'm going to write x to the 4th. Does that make sense? Okay. And then I'm going to write plus what? Well, now it says x to the n minus 2. So I'm going to write x to the 3rd. And I'm going to write a, because that's part of the formula. And then I'm going to write x to the, well, it's n minus 2. Oh, no, now we want n minus 3. So second, yeah. X squared, and we're going to write a squared. And then it says dot, dot, dot. The powers of x are going down. The powers of a are going up. So we're going to get x a cubed, and we're going to get a to the 4th. And I'm off the map, but there we are. Does that make sense? So that's my first step. Now I cancel the x minus a's. So I get the limit as x approaches a of, well, that big parentheses is all that's left now. X squared a squared plus x a cubed plus a to the 4th. Sorry about the mess there. All right. Am I allowed to plug in a now? Yes. Okay. I would say that this function, to use my word from next week, this function is continuous at x equals a, right? The old fraction wasn't. You couldn't plug in a or you'd be dividing by 0. But this function is continuous at x equals a. It's almost like we had the whole we colored in, a removable discontinuity. And so I go ahead and I substitute in a for x. Let's see what we get. We get a to the 4th. We get a cubed times a. We get a squared times a squared. We get a times a cubed, and we get, well, we already had a to the 4th there. So what do you have? A to the 4th plus a to the 4th plus a to the 4th. Okay. So what do we get? 5a to the 4th. And I think that's the answer in the back, right? That should be the answer. So for 81, we want to find a polynomial such that the limit as x approaches 2 of this polynomial equals 6. Okay. Well, let's see what we could do here. I mean, they tell me a few things. So, I want you to see it. There it is. P of x for 81 is a polynomial x squared plus bx plus c. What do we need? We need the limit as x approaches 2 of this polynomial divided by x minus 2. Is this limit supposed to exist? Yeah. It's supposed to exist and actually equal 6. But the fact that it's going to exist tells me something about what we want to have happen with this polynomial. What do we want to have happen? We want it to be that you can take that polynomial and you can factor it. Okay? And what do we want one of the factors to be? Why? It has to be able to cancel out with x minus 2. You guys follow that? So we need this. We know we need this to be x minus 2. That's your first hint. Matter of fact, if you knew what you wanted the other factor to be, you'd have it. Right? Because then you could just multiply these together, you could see what b and c equal. So do we? Do we have any idea what the other factor should be? Well, think about how these problems work. You're going to try to get 6. How? You're going to do this. You're going to write limit as x approaches 2. You're going to have x minus 2 times something over x minus 2. This is x, I don't know what it is yet, right? Minus unknown. I don't know what it is. But these x minus 2's are going to cancel. And then what are you going to do? You're going to plug 2 in where? 2 in for the x, right? So you're going to get this little equation. 2 minus, I don't know, equals 6. I would say you have enough information at this point, right? You could figure out what the question mark is. Once you know what the question mark is, you can come back here, figure out what that is, and you can figure out what b and c are. Okay? I think that's enough info for that one. Okay. 82. A problem from relativity theory. The theory of relativity. Who did that one? All right. Well, this is the Lorentz contraction formula. Okay? So it says that something moving very quickly will look smaller than it actually is. As you get close to the speed of light, it'll look smaller than it actually is. How much smaller? Well, it depends, right? So, I mean, just to get an idea of how that formula works, you know, if I put in a really small velocity, okay? So, well, I guess in order to use this, we're going to need some values. C is the speed of light. Do you guys have a value for me for the speed of light? And then we're out of luck if we don't have that, right? What's that? 3 times 10 to the 8th meters per second. I've heard that before. My father used to tell me it's 186,000 feet per second. Okay? He was an engineer, so we had these kind of discussions at times. So, anyways, if here's C, whatever that is, right? If I throw this into the formula, and here's V squared. Okay, let's see if I can answer some of these questions. It says part L, or part A. What is the observed length of the ship if it's traveling at 50% of the speed of light? Oh, thankfully, I guess I don't really need to know what C is. I was wrong. Because they told me, so in part A, we are given that the velocity is equal to 50%, so 0.5 c. Right? So I can do that. I can just substitute that into my formula. And the question is, what can you tell me about the new length? Well, L is going to be L naught times 1 minus, this is 0.5 c squared here over c squared, right? And now if I simplify, I can write this as, well, 1 minus, and this is just a half times a half, which is 1/4. And I have a c squared in the numerator, and I have a c squared in the denominator. Am I right? You guys with me? Okay. So what am I going to do next? We cancel the c's. We get L naught times the square root of, well, 1 minus 1/4 is 3/4. And so I think what I just determined, see, this is L. L is going to be L naught times radical 3 over 2. Right? So what's radical 3 over 2? We should get a decimal value. Calculator. That's certainly a number I see a lot. Here, let's do square root of 3 divided by 2. 0.866. So we're at about 87% of the actual length. It doesn't look as long as it actually is. My kids just watched Jurassic Park. Objects may be closer than they appear in the mirror, right? I mean, that's kind of what's happening here. So that's part A. And then they asked me to do the same thing for part B. And it says, in parts A and B, what is happening to L as the speed of the ship increases? Well, again, when you go faster and faster, L is going to look smaller than it actually is. Now, part D. Find the limit, blah, blah, and explain the significance of that limit. All right, I think that's worth thinking about. So let me just jump to D, and then I'll be done. Because that's where the calculus is happening, right? When we start doing limits. D. So this says limit as V approaches C from which side? Is that important that I say from the negative side? Because there's an idea that you can't go faster than the speed of light, right? So we're going to approach the speed of light. Like Einstein said, you can't do that. You can't surpass the speed of light. Well, let's see what happens. We have 1 minus v squared over c squared, right? Okay, so what do? How do you compute this limit? Well, we replace the v with c. Are we allowed to do that? We're allowed to do that if the function is continuous, right? Now, do you guys know anything about the square root function? Y equals square root of x is defined for x greater than or equal to 0 too, right? Isn't that true?
It is.
And so, as long as that's true, and I'll zoom out so we can see everything, then I guess I just have to check, as I put in values of c, am I going to stay bigger than 0? Well, I am, because I'm not really putting in c. I'm putting in a number slightly smaller than c. And so this fraction here is a little bit smaller than what? 1, right? And so you can do this. It's continuous all the way to, I mean, if you graph y equals square root of x, it's a parabola that opens up sideways and ends at 0, right? So what I'm really doing here is I'm picturing, as I approach c, yeah, you get L naught times the square root of 1 minus c squared over c squared. So you get L naught times the square root of 0, which of course is what? So what's the significance? As the velocity got closer and closer to the speed of light, we would look at the spaceship and we would say its length is getting closer and closer to what? 0. So it would vanish if it went the speed of light? That's pretty remarkable. Anyways, I think that's a cool problem. So I'm going to do a few sample problems with you in a minute, I think. But just to get an idea, we talked about 1 over x, right? I really like this example to talk about infinite limits, 1 over x squared. It's kind of like the 1 over x graph. Matter of fact, on the right-hand side, it looks very similar. On the left-hand side, the big difference is you have things above the x-axis because why? You're squaring it, so everything's positive, right? And so again, it doesn't matter if you approach from the left or from the right. As x gets small, y grows without bound. From either side. You guys see that? So again, what does that mean? It means that we are going to say the limit exists for this problem. So again, the picture, let's make this big. When you have y equals 1 over x squared, and from either side you approach that, we're going to say the limit as x approaches 0 from the negative side of 1 over x squared is 0, and we're going to say the limit as x approaches 0 from the positive side of 1 over x squared is 0. And so that's the only time that we're going to say the limit as x approaches 0 of 1 over x squared equals 0. We're going to say that. Okay?
Positive infinity.
Oh my gosh. All these are wrong, aren't they? Start all over. Luckily, we can delete all that. Is that all recorded? Yeah, we'll delete the 49th and a half minute. As we were saying, the limit as x approaches 0 is positive infinity when you're coming from the left-hand side. And that means it grows without bound. The limit as x approaches 0 from the 1 over x squared from the right-hand side is positive infinity. And that's the only time that we're going to say that the limit as x approaches 0 of 1 over x squared is also positive infinity. This okay now? Thank you. You guys got to keep an eye on me. All right, so I thought I might do a few practice problems with you. One of the reasons to study these functions is that a lot of the trig functions have reciprocals or have something in the denominator, and so you run into asymptotes, okay? Now, I know you know the graphs of sine and cosine are waves, but for example, let's take tangent function, right? Let's do that one. So if we have y equals the tangent of x, let's talk about that. And if I said let's sketch a graph of tangent of x, well, from your trig identities, tangent of x is the same as what fraction? Sine over cosine. So we're going to call this the sine of x over the cosine of x. Okay? And so I guess the next question is, well, if I have a cosine of x in the denominator, okay, I want you to notice, okay, this function is undefined when the cosine of x is 0. Right? When does that happen? Well, to know when that happens, you want to look at the unit circle. And you want to remember that, you know, the places that it's going to happen is when the x-coordinate on the unit circle equals 0. So if we're pointed straight up or if we're pointed straight down, right? So undefined when x equals things like pi over 2. What else? 3 pi over 2. What else? Are there other values? Yeah. 5 pi over 2. Of course, that would be swinging around again. Or you can go the other direction, plus or minus these things. Okay? So if we're going to sketch a graph, we have to pay attention to that. Okay? So now, the tangent function, you may remember this because, well, you just had a trig class not long ago, most of you. And so the tangent function ends up having asymptotes at pi over 2. It ends up having an asymptote at 3 pi over 2, 5 pi over 2, negative pi over 2. Right? The tangent of 0 is... What's the tangent of 0? Well, it's the sine of 0 over the cosine of 0. What's the sine of 0? 0. And what's the cosine of 0? Cosine of 0 is 1, right? So if we have 0 over 1, 0, right? So if I start to draw the graph, it's going to look like this. It's going to go through 0, 0. And anyways, you get kind of a picture like this. And it's periodic. It's going to go through pi comma 0 also. You get this repeating pattern. So what could we ask you about the trig function now that we couldn't have asked you in a trig class? Well, now we can talk about what happens at the asymptotes. So what I'd like you to do is to see if you can spend a minute writing a statement about the limit as x approaches pi over 2 from the left side for tangent of x, from the right side tangent of x. Why don't you guys spend a minute on that with someone near you, see if we come to an agreement of what should happen here. So we're going to say that this guy, this limit is, as I approach from the negative side, this is positive infinity. As I approach from the right-hand side, this is negative infinity. Okay? So does the limit exist? No. We would need that situation like we had in 1 over x squared. Okay? I think, honestly, this is probably all you need for this section. So I'm going to kill it.